All right, what's up, guys? In this video, we're going to pick up some calculus here. It's going to be another integration practice video. This is going to be example number 59 of the integration practice series. All right, so we need to evaluate the integral dx over the square root of x squared plus 144. So it's a little difficult to see. I do apologize, but that is the square root of x squared plus 144. So this is the perfect time to do a trig substitution. And this is a tangent substitution, obviously, because if you notice here, what we have is the square root of x squared plus a squared. And remember that trig substitutions don't have to be under square roots. Most are, but they don't have to be. And also keep in mind that addition is commutative, so x squared plus a squared is the same thing as a squared plus x squared. So in this case, this is a tangent substitution. So if we have this form, we know that x is going to be equal to a tangent theta. So now what we need to identify is, what is a? Well, if a squared is 144, and that must mean that a is 12, because 12 squared is 144. So that means that the appropriate substitution here will be x is equal to 12 tangent theta. So we now need dx, which will be 12 secant squared theta. Don't forget to multiply by d theta. And then we'll go to our integral. And I don't skip steps in my videos, always go through all the steps, so I'll write everything in. So we'll get 12 secant squared theta on top there. All we're doing is replacing the dx with that. And then down here in the denominator, we'll plug in our 12 tangent theta. That's being squared, and then we add that to 144. And this is all being integrated with respect to theta. So now we clean up the square root. If you notice under the square root here, we have the square root of 12 tangent theta squared plus 144. So that's going to be 144 tangent squared theta, because we're squaring not only the 12 but also the tangent theta, or the tangent rather. And then we simplify this, and we can write this as 12 times the square root of tangent squared theta plus 1. And remember that the square root of tangent squared theta plus 1, we can write that as the square root of secant squared theta. Square root of secant squared theta is secant theta. And we still got the 12 out there, so this would be 12 times secant theta. After you do the simplification, all you do is use a Pythagorean identity for that. So we then go back to our integral here, and we look at what we got. So we got 12 secant squared theta. And then we got 12 secant theta down here after we clean everything up. And it's going to be d theta. Now the 12s divide out to 1. One of the secants goes away. We still got one left over because we got 2 up here and 1 down here. So now this just becomes the integral of secant theta d theta. Okay. Now we know that the integral of secant theta, or the antiderivative of secant theta, is ln absolute value secant theta plus tangent theta plus c. Also recall that some textbooks may write it as ln absolute value tangent theta plus secant theta plus c. But recall that it doesn't make a difference which way that it's written. These are the same thing because addition is commutative. So secant theta plus tangent theta, the same thing as tangent theta plus secant theta. So Either way that your book writes it is perfectly fine. Very similar to how we talked about up here. We talked about the trig substitution. We talked about, in this particular case, we get the square root of x squared plus a squared. Well, if it were 144 plus x squared, well, it would still be a tangent substitution because addition is commutative. And what commutative means is it says the order doesn't matter. The order doesn't change the solution. A perfect example of this is 2 plus 4. Well, 2 plus 4 is 6, you know? And, well, what's 4 plus 2? Well, 4 plus 2 is also 6. Multiplication is also commutative, so 4 times 2 is 8. Well, so is 2 times 4. So that's what I mean when I say commutative. So I just wanted to rehash that. And so now this is what we get after we've taken care of the integral. Now the goal is to find, we need to find the trigonometric ratios for tangent theta, secant theta. So all we do is just use a little bit of trigonometry for that. So remember, and well, use SOHCAHTOA actually, which I'll write over here. SOHCAHTOA, remember, from trigonometry. Okay, so we know that tangent theta, that's opposite over adjacent. And remember that secant theta is the reciprocal of the cosine. And so secant theta is hypotenuse over adjacent. Because cosine is adjacent over hypotenuse. So reciprocal of that, which would be secant theta, is hypotenuse over adjacent. So what we do now is we go back to our substitution at the beginning and we see what we have. So given that x was equal to 12 tangent theta, that means that tangent theta is equal to x over 12, which means that we now have both the opposite side and the adjacent side of this right triangle. So we'll have tangent theta is equal to x over 12. So that means that the opposite side is x, the adjacent side of the right triangle will be 12. Okay. Now we do need secant theta, which is hypotenuse over adjacent. And if you notice, the only side that we're missing for the triangle is the hypotenuse. So that's when you use the Pythagorean theorem, a squared plus b squared is equal to c squared. And remember that c is going to be the hypotenuse of the right triangle. So all you have to do is just substitute everything in. So if you sub everything in, you'll get x squared plus 144 is equal to c squared. And if we solve for c, which means that we take the square root of both sides, we'll get c squared is equal to, we get c, is equal to the square root of x squared plus 144. And that's the value of c, and that's the value of the hypotenuse. So you take the square root of both sides, because if you take the square root of c squared, you get c, which is what we need. Okay, so hopefully that makes sense so far. Now, drawing the triangle isn't, I'll put it right there. Drawing the triangle isn't required, but it does give you a little bit of a feel for what we were looking for. So this is the right triangle, of course. We now have the value of the hypotenuse now, which is the side that we're missing. Hypotenuse is always going to be, for the right triangle, it's going to always be the longest side of the triangle, or the side of the triangle that's directly across from the right angle. And we also have the adjacent side already. The adjacent side was 12, and the opposite side was x, remember? So that means that secant theta, which we know was hypotenuse over adjacent, would just be the square root of x squared plus 144, all divided by the adjacent side, which was 12. So when we go back to the integral that we did, we can now put the ratios in there. So it'd be ln absolute value. Now we know what tangent theta was. Remember, that was x over 12. Now, they both have a common denominator of 12. So if you want to, you can put them both over each other. So if you want to write it this way, if you just want to write x over 12, and then plus the square root of x squared plus 144 all over 12, and then plus c, that's obviously fine. But we have a common denominator of 12. So you could more write it as ln absolute value of x plus the square root of x squared plus 144 all over 12 and plus c. Okay, and you could write that as your final answer. You can clean it up a little bit, and it will give you your answer. So your final answer for this integral so we're asked to integrate dx over the square root of x squared plus 144, and our answer for this is going to be ln. I'm going to kind of clean it up a little bit. I'm going to write it as ln of 1 over 12 absolute value of x plus the square root of x squared plus 144 and then plus c. And that would be your answer. Alright, so hopefully that makes sense. Again, I've done plenty of videos on trig substitution, so obviously this isn't the only example that you can look at for a little bit of review on the trig substitution. Okay, so let me know if you got any questions. We could talk about it, but I'll see you guys next time.